of the subject nonetheless. And as I said in the first lecture, we're interested in sort of developing mathematical methods to understand problems in science, in particular problems involving multiple scales and the formation of microstructure. But, and I'll say a little bit about this, but the aspects I talk most about today is actually in the different direction. If you like to divide mathematics in pure and applied, which I personally don't like so much, then you could view this sort of as an application of applied mathematics to pure mathematics. Okay, so also I should say that sort of in as far as I talk about my work, it's a result of a long-going cooperation with Vladimir Schwerak in Minnesota, and our work was strongly inspired by Luc Tatar's program, if you like, to study oscillation and concentration effects in nonlinear PDE, which started in the mid and late 70s with the method of compensated compactness. And on the other hand, we strongly benefited from Gromov's work on convex integration and the H principle. I think I only understand a small aspect of that, but that was enough for us to make progress on some things. And so as I said, since there will be a number of topics here as a brief outline, so I'll first say a few words about sort of crystal microstructure and what some of the mathematical problems are in analyzing it, and then I'll focus on one of those problems, and I'll talk about convex integration. And before I talk about the methods, I'll give you sort of some examples of what you can prove using the method. Then I'll talk a little bit about the method, and we recognize it's not quite good enough to do, in some cases, what we really want to do. And then we come to the last topic, which has to do sort of with notions of non-standard notions of convexity in matrix space, and there's some interesting linear algebra and combinatorics, which eventually leads to sort of interesting solutions of elliptic PDE. Okay, microstructure. This is a picture of a single crystal of a certain alloy, and so you see the different colors actually correspond to different crystal structures. And just to give you an idea of the size, so the size of the whole picture along this line is a bit more than 1 millimeter. So and these pictures come from the lab of Richard James at the University of Minnesota. Here's another one which shows a pattern which is very often observed. It's called layers within layers. So you have certain bands here, and then you see they form super bands, and sometimes you can even have 3 or 4 levels of this hierarchy. You can also have different structures which sort of look even more like piecewise linear maps. And also the structures can occur on many length scales down to the atomic length scale. So the picture there is roughly 1 millimeter. This picture here is factor 1,000 smaller. It's a bit less than 1 micrometer. And here we have so-called atomic resolution microscopy. So we're talking yet another factor 1,000. 1 nanometer, and on this picture, maybe I can move it over here, on the picture on the top, every dot is an atom. So that's what modern microscopy can resolve, or more precisely, every dot, of course, is a row of atoms, because we're looking at a crystal, and the interpretation of this picture is not completely obvious, because what you really get is you get some X-ray pattern, and then you have to sort of inverse Fourier transform to get it back into real space. That's what you get out. And there you can see very nicely that this looks really like a piecewise affine deformation. You see there's a shear up and a shear down, and the numbers at the bottom give you sort of how many atoms are in each layer, and you see that it's very regular, at least in that particular case. So here are some natural questions. What does this microstructure consist of? Why is it so fine? And sort of how could we possibly derive mathematical models to describe it and to learn something about it? Okay, so what does it consist of? That's relatively easy to say. So what this material do is they undergo a so-called solid-solid phase transformation. So these are crystalline materials. So they're a repetition of a periodic cell. And depending on the temperature, the form of that cell changes. So the simplest case I've drawn here at high temperature, you have a cubic cell. And then as you go below a certain critical temperature, you stretch one axis of the cube, and typically you shrink the two others, and that's sort of called tetragonal. And then, of course, you have three different variants. So if you like, the different colors you saw in these pictures corresponded to different variants. And if you want to describe this, say, by transformation, it's natural to take the cubic phase as a reference. Then this you would describe by the identity map, and well, these are described by certain diagonal matrices, and of course you can then post-multiply by a rotation because rigid motions in space are always possible. How does this lead to these belts you saw? Well, I've tried to illustrate this here sort of in two dimensions. So originally we have the square lattice, and this can stretch in one direction or in the other. And actually, if you sort of cut these out on a piece of paper, and then you try to match the blue and the green one, then you see that there's only one particular normal along which you can do this in such a way that sort of the atoms here fit on each other, so that you don't have a mismatch along the line. In fact, there are sort of 2 or 4 normals, but they're all symmetry related. And we'll see this kind of bands later in a more analytical setting.
So what really happens in nature? Somehow it's randomly each cube changing to this, or do we some...
Okay, that depends a bit. Often what happens is that when you really take a specimen, a single crystal, and you carefully cool it down, usually the new phase comes in from the boundary, and then sort of it marches through. And so you may form, say, so here then I should have actually drawn also the original black phase, which in this case, however, is not compatible with these two. So you would form sort of a little, near the corner, you would form a little bit of this, and then this would march through and eventually fill the whole thing. Or if you look at this, what probably happened here is what you kind of had in mind, that in different regions these bands form, and in this case there are 2 natural normals along which they can layer. So in some regions they formed in that way, in some regions they formed the other way, and then as they grew they eventually realized that they had to match, and here they cannot be perfectly happy. So here you have to create some stress, and you actually see they sort of branch into a finer and finer mode. I hope you can see that. So you see they kind of start to split here, and here's another split, and near the end you have this kind of comb-like structure. And this actually we also made a simple model to analyze this, but this would be a separate talk. So yes, it usually forms locally in one of the possible patterns, and then sort of the more complicated patterns evolve. And you can induce these changes by temperature, but also by applying stress. And so the second one is actually more reproducible and gives you, because the stress you can apply in different directions, so it gives you more multidimensional control parameters. So what is the mathematical model? So the model was developed by Ball and James, and more almost parallel by Chipot and Kinderlehrer. And really this idea that you can treat crystals by sort of continuum elasticity, I think goes back to Ericsson, who sort of strongly advocated this. So the energy is similar to what we had in the first lecture. It depends on the deformation gradient of the elastic deformation. And For the moment, I also indicated explicitly the dependence on temperature. I'll drop that later and work at constant temperature. And sort of very schematically, sort of at high temperature, the energy would have only one minimum, and at low temperature, it has multiple minima. Of course, in addition, you always have the rotational symmetry, but that's hard to draw in a one-dimensional axis for the deformation gradient. And you see immediately from this that the functional is non-convex, and it's even worse, it doesn't satisfy neither of these weaker notions of convexity. So if you like, the corresponding Euler-Lagrange equations are no longer elliptic, not even in the weak things, but they're really mixed elliptic hyperbolic. So that would be a very hard problem to treat, and so people often make the simplification that they essentially, instead of looking at minimizers of the integral, they look at pointwise minimizers of the integrand. So deformations which only live at this minimum point or very close to it. And okay, this obviously simplifies the problem by going from second order to first order, but there's also some reason for this in terms of modeling. So first of all, in practical materials, sort of the energy wells out of the minima are very steep compared to the forces to which you want to apply. And the other thing is the position of these wells, which just have to do sort of with the transformation parameters. They're very well known. These parameters you can measure to 4 digits by sort of X-ray diffraction, whereas the rest of the shape of the energy landscape is not known so well. I mean, this would require very precise measurement to know exactly sort of what the potential looks like in between. So in terms of modeling, it's also not such a bad idea because you're only using part of the information, and if you can extract already something from that, that's again more likely to be robust. So anyhow, that's what we're going to do. So I've repeated, so I now drop temperature and I normalize the energy so that by a constant so that its minimum is 0, and I call K the set where the integrand attains its minimum, and I'm looking for elastic maps U from Rn to Rn, or I could even generalize to Rn. And then, so what I said there as the constraint theory would correspond to what I call exact solutions here. So I'm looking for deformations whose gradient almost always lies in this set of 0 energy. And okay, correctly speaking, I look for Lipschitz maps, so the gradient can be discontinuous. Then they have a differential almost everywhere, and so therefore I require this condition to hold almost everywhere. Then if you want to study these crystals, there are at least 2 other equally natural questions. Namely, one is to look for almost 0 energy solution. I mean, remember, this was quite a drastic simplification, so we certainly should allow, to have a little bit of energy. So mathematically, this would mean to characterize sequences such that the gradient converges to the set K and they're uniformly Lipschitz. And a closely related question would be to characterize the effective property, namely to look for those sequences which are compatible with certain affine boundary conditions. So if the matrix F belongs to this set K, of course you can just take the affine deformation itself, but it could very well be that by making these very fine mixtures, you can get convex combinations of certain matrices in here, so therefore you can get a much larger set where you can achieve almost 0 energy, and that much larger set is very much responsible for the effective properties of these materials. And so today I'll only talk about the first question. And if you want to know more about the other things, I wrote sort of a little set of short lecture notes where you find many further references, and there's also a very recent book by Georg Dolzmann which just came out in Springer Lecture Notes. Okay, end of part 1. So the rest of the talk will somehow be centered around these questions and about the method of convex integration to attack this question. And before I explain the method, I sort of want to explain that I want to sort of show you that it could be an interesting method because it produces interesting results. So the first example I want to talk about concerns elliptic system, and here I've just sort of summarized some generalities. So there also we now look for map U from Rn to Rn, maybe related to elasticity, maybe not. Then we sort of prescribe a smooth function from the matrices to the matrices, which in elasticity would be the stress. And then we want to solve this second order equation. So we take the divergence with respect to rows. So we get a system of m equations in m unknown functions. System of second order partial differential equations. And this system is called elliptic if the linearization is well behaved. And well behaved means that it should have no plane wave solutions, or by Fourier, no one-dimensional oscillations. Because if you had a one-dimensional solution, then you could also make very high frequency of solution, then you don't want. And so then, as you will know, in the scalar case, so when we only have one function and one equation, then the famous theory of the Georgi and Nash, and later developed by Moser, tells you that all weak solutions of this PDE are actually smooth. End of story. And in the vector case, this turned out to be more complicated. About 10 years later, people found the famous counterexamples. The counterexamples under additional assumptions are not so bad. So for example, if you take a strictly monotone sigma, say the gradient of a convex function, then you can still prove that U is smooth up to a very small closed set. So you can have singularities, but they sit on a closed set. But now here is something more recent, which is a much more dramatic failure of regularity. So that's John work is slightly clever. So what we say, there is a smooth, strongly elliptic system in that sense that has solutions which are Lipschitz, but they're nowhere C1. So in other words, the gradient exists, but in the neighborhood of every point, it has high oscillation. And there are also Lipschitz solutions with compact support, so there's certainly no unique continuation theorem for this, which again, for scalar equations you have. And in fact, this system is variational, so it arises as the Euler-Lagrange equation of such a function. So sigma would just be the derivative of the scalar function f. And this function f is not only elliptic, it satisfies a stronger condition which is called quasi-convexity, and I don't want to explain it in detail, but quasi-convexity is a sufficient condition for existence of minimizers for this problem. And for quasi-convex integrand, Evans showed in a classical paper that if you look at the minimizer of this functional, then again it's partially regular, so it's regular outside a closed null set. So what our result says is that when you consider just solutions of the Euler-Lagrange equations rather than minimizers, then the mere solutions can be much, much worse. So, and actually Evans's result was recently extended by Christensen and Terhary to also to local minimizers. So there's a parabolic version of this result. Of course, there's a trivial parabolic version. You could extend the solution constant in time, then it solves the corresponding parabolic system. But of course, what you want for the parabolic system is you want to start with smooth initial data and see whether they can become rough in finite time. And so here the assertion is you can do that. You can start even with zero initial data. But in this case, we don't know yet to get zero right-hand side, but we can put the right-hand side in a Hölder space. So you would expect that the solution should have two spatial derivatives in the Hölder space and one time derivative in the Hölder space. But what we construct is a solution which is Lipschitz in space-time, and again, the spatial gradient is nowhere continuous. And so formally, So the sigma is actually the same as before. So formally, the system is the gradient flow of the corresponding variational problem. But actually, for the solutions we construct, the energy inequality is not satisfied. So an interesting open problem is if you have sort of, say, a suitable local version of the energy inequality, whether that would give you better results. That's not true. So here's a completely different example, which you may find amusing and which was sort of raised in the original paper by Paul and James on crystal microstructure. So this is a much simpler problem. No PDE. We're now giving a finite number of matrices, and we require that the difference is never rank 1, and I'll explain in a second what the significance of that is. And the question is whether we can find a non-trivial Lipschitz map, so one where the gradient is not constant, whose gradient only uses these finitely many matrices. And there are, of course, simple examples, namely, we take one gradient on one side of a hyperplane and another gradient on the other side of the hyperplane, but this can only be Lipschitz if the tangential derivatives are all the same. That's exactly, actually, the analytic version of this matching picture. And this can then only happen if these matrices differ by rank 1. So that's a situation we want to exclude. That's too easy. So we make the matrix in such a way that you can never have a planar interface. In fact, then by the blow-up argument, you can never have a piecewise smooth interface between the different regions, because otherwise you could go to a point where it's smooth or rectifiable and blow up, and after blow up you would reproduce the situation, and so you would violate this condition.
So again, this question is, how many matrices you can find for the range of the differences?
No, the question is whether you can find any finite set of matrices and a map such that the gradient of the map takes only these finitely many values. And I want to exclude sort of the trivial case that two matrices differ by rank 1, because then you can clearly find a non-trivial map. So somehow, if everything was piecewise smooth, such a map could not exist. Well, I mean, like it could only take one, it would take exactly one of the gradients. Are totally unrelated.
So even when it's smooth, you can still make a non-trivial if the difference in rank is 1.
Piecewise.
Yeah, so, okay. So maybe what
it's obvious.
So that was, no, say this is your domain, and what I was saying is the condition I put of this non-rank 1 connection immediately excludes to have a picture, say, like this. Because if you had a picture like this, you could go to this point, you could make a blow up, and then you would have a situation where you have A1 here and A3 there, and that would imply that rank A3 minus A1 is 1. So you can certainly not have something sort of, the partition of the domain cannot be into piecewise smooth or piecewise polygonal or something like that. So it could very well be that that it's not possible. No? Okay, so here's the answer. So this is essentially due to Bernd Kirchheim, and he actually solved the problem completely in joint work with David Price at UCL. He showed that if you allow to give yourself 5, so they have an example of 5 matrices such that there is a non-trivial map, and they, together with Miro Klebik from Bratislava, he also showed that with 4 it's never possible.
And given, say, 5 matrices, we want to decide whether it is possible, whether it is not.
That's not so easy, but in some sense, let's see, is there example generic? I think at least it's open, so you can perturb things a little bit. But no, it's not so easy to decide.
And this is in dimension 2.
Yeah, okay. Actually, you can show quite easily that it's enough to consider the 2 by 2 case. Because if you have an example in 2 by 2, you can lift it trivially, and you can also show that for the other direction, it's enough to consider 2 by 2. So, okay, so these were 3 examples what this theory can do for you, and sort of in very general terms, in some sense, the main idea is to sort of reduce solving a PDE in real space to sort of looking for certain algebraic or linear algebra features in matrix space. And as you see, that will lead to certain new notions of convexity, and of these we only have a very limited geometric understanding. And so just to close the second part of the lecture, I want to point out that the second order problem, of course, can be written in this first order framework, in which I will from now on always work, because if we're in 2 dimensions, then the divergence of sigma being 0 is the same as sigma being a gradient if we perform a 90-degree rotation. So if I introduce sort of a new variable, which is now in R4 rather than in R2, then I can express the whole problem as a first order problem, sort of with a set K, which is now a graph, if you like, it's a 4-dimensional graph in the 8-dimensional space of 4 by 2 matrices. Okay, so now I finally have to say what this convex integration is. So here's a quick overview of the history. So really it started as often with an example. Yeah. So as often it started with an example, and the example were these kind of famous wild isometries by Nash. As you probably know, if you consider the standard sphere as 2, and you want to embed it isometrically into R3, so isometrically in the sense that on each tangent space you have an isometry for the differential, then there's a classical theorem of Hilbert which says if you want to see 2 isometric immersion, then it's rigid. And you only have the rigid motion, so there's no way to deform the sphere isometrically. But what Nash proved, if you go to C1, where isometry still makes perfect sense, then you can map the sphere isometrically into an arbitrarily small ball in R3. So you can somehow crumble it in a way which is C1 but not C2. And then sort of Gromov realized that there's sort of much more general idea behind that, and he worked mostly with C1 map, but he also had some remarks about Lipschitz maps, which are more interesting in the context of today's lectures, and sort of Vladimir and I then sort of gave a short self-contained proof of the Lipschitz case, and then a number of other people contributed, and I'm happy to say more in private about this. So the setting is, again, we're giving a set K, typically compact, we're giving a domain in Rn, we're giving a map U0, which you should look as a boundary condition, so think of affine map, it's enough for this talk. And we look for Lipschitz map, which takes gradient in K, and sometimes we require that it also takes certain boundary conditions. So, okay, now I'm missing one slide. Okay, so, and the idea of convex integration is to start from simple one-dimensional constructions and then build them up by iterations, like these layers within layers which you saw in the crystal pictures. And so on this slide I tried to put in parallel somehow what happens in real space, what happens, if you like, for the PDE, and what happens in matrix space, so you get some feeling for this kind of relationships. So let's go back to the case where we only want to use 2 gradients. We already know that's only possible if the matrices differ by rank 1, and you can also see easily that the only solution in these cases are solutions where the gradient only changes in one direction, namely in direction of this normal nu. So that would be the picture in real space. You have certain bands, and the gradient is constant on these bands. In matrix space, I want to symbolize this in such a way. I have A and B, and the line in between means I have a rank 1 line. These two things are rank 1 connected. Now when I want to iterate this construction, I somehow need a more local version. I need to be able to put blocks together. So for example, I would want to construct a map which, say, outside here has some gradient f, which is a convex combination of A and B, and where inside I essentially only use A and B, because then I could hope to iterate. And this you can almost do. So what you would do, of course, you would put A and B here in a very fine layering, but then, so this looks like a corrugated roof, except it's not round but has sharp corners, and eventually you want to match it to something affine, so you need a thin boundary layer to match it. If you do this matching carefully, you can see that you can do this in such a way that the gradients you use here don't stay exactly on this line, but they stay arbitrarily close to this line. So in some sense, you could view this as starting from the matrix F and replacing it not quite by A and B, but by a small neighborhood of A and B. And so the essence of convex integration now is to iterate this.
Why is the name integration?
Okay, that's that question you should really ask Gromov. So I think, okay, I could tell you why I think it has to do with this integration of measures. Why it has to do with integration, I mean, that really defeats me. So the idea is you could look sort of at the distribution function of the gradient, so that will be a certain measure, and so somehow you start from a Dirac mass here, and you sort of replace it by a measure which is kind of smoothly distributed on this line, or on the slight neighborhood of this line, and I think he thinks about sort of integration of this measure. But that's like, say, with viscosity solutions, which have some connection with viscosity, but certainly for second order equations, there's no viscosity at all. Okay, so what is the essence? So the essence is to iterate this construction and to apply it in many different directions. So, and of course, on the PDE level, that would correspond to more and more complicated pictures. But on the level of matrices, it's not so bad. I mean, it's essentially like sort of building a tree backward. You start from something, you split it, and then you can split this again, and so on. So here, sort of little indication if you were doing this for a scalar problem, where the gradients are, say, the gradients you want in the end are the four corners of the square, and the one you start with is say, in the convex hull. Then maybe in the first step, you would split it into these two things, and then each of them would be split again, and this way you can closer and closer to the 4 points, and then there's sort of an extra trick to get you exactly into the 4 points. And in higher dimensions, for non-scalar problems, it's similar, but then the natural notion is not convexity, but this is convexity along rank 1 lines alone, because only along rank 1 line you can perform this construction with a gradient. So let me first explain how you actually do it when the set you want to end up in is open. You see that openness, of course, helps because here you always have to make a small perturbation. So for this, I want to define what I call the lamination convex hull. Gromov calls it the P-convex hull because some operators call it P. And you can think of this in two ways, as usual. One is to build it up iteratively. Whenever you have 2 points in your set, which are rank 1 connected, then you add the whole rank 1 segment, and you repeat the process. And in contrast to ordinary convexity, this need not stop after finitely many. You may have to do it infinitely many times. And the other definition, of course, is you take the smallest set which contains a given one and is closed under this observation. So and here's the result. So suppose you're given a set U where you want to be the gradient in, and you're giving an affine boundary condition which lies in this hull, then you can produce a map which has the gradient in the original set, has the right boundary conditions, and is arbitrarily closed in the C0 norm. So if you like, you can think of this as a C0 fine approximation. So the moral of this construction is that you take the gradient, you take the boundary condition in the larger set, and successively you push back to the set where you want to be. So, and the proof is more or less induction over this picture. And openness helps you sort of to allow yourself this little bit. Now all the interesting sets are not open. So then you need some extra trick. And this is what Gromov calls an inapproximation. And the best way to think about an inapproximation is to assume that your set was S2, then you were just solving the Iconal equation. Of course, that's simple. And you want to approximate it by open sets from the inside, so to speak. So you take sort of a sequence of annuli which becomes thinner and thinner, and in the end shrinks to the S2. And so the general definition is that the sets have to be in such a way that this new kind of convex hull of the successor contains the predecessor. And then the result is if you start with the first set in the sequence, say with a ball of half the radius, and the boundary condition is there, you can always push back to the next guy, and in the limit you converge to the set. That's actually a non-trivial and in fact a first surprising fact, because as you see, this construction is made by building more and more oscillations. So you would think that when you pass to the limit, it will only be a weak limit, and instead of the oscillations, you only see the average, so everything is lost. But when you do it the right way, then actually this does not happen. Somehow you have to choose the oscillations very carefully in the next step. Or you can, there's also an abstract way to see it through a bare argument, or if you're familiar with martingales, it's sort of a bit like sort of the martingale theorem, where you also always split things, and then in the end you get a limit distribution. So now we have a way to do general sets, and sort of just to sum. And okay, now you may ask, when is it possible to construct such an inapproximation? And again, you should take the sphere as a kind of guiding example. It's possible, roughly speaking, if this lamination convex hull of the original set is big enough. If it's big enough to, say, contain open sets, and then you can shrink the open sets back towards your set. That's kind of a meta statement. In practice, we sort of prove it for each case by hand, but that's usually not so difficult. So just to repeat the moral of what we've done so far, in some sense what we've learned, if this lamination convex hull of our set is sufficiently big, then we can construct many interesting solutions of this PDE, and in particular solutions which are very highly oscillatory. I will not explain this in detail, but once you get one solution of this, in fact, you get a bare fat set of them, and in particular you get ones in there which have arbitrarily high, I mean, where the oscillation is large in the neighborhood of each point. So here are some examples to which you can apply this to. You can apply it to scalar problems. I will just focus on the middle example, which is isometric emulsions. So you look for map whose gradient is an isometry, but in contrast to the first talk, it will not be a proper rotation. It can either be a proper rotation or a proper rotation plus a reflection. So say in 2 dimensions, if I take a sheet of paper, I'm now also allowed to fold it. And what this theorem says, that whenever your boundary condition has Lipschitz constant strictly less than 1, then you can find a map whose gradient is an isometry almost everywhere. So in particular for this piece of paper, this means that the boundary condition, for example, could be identically 0. So there is a Lipschitz map which maps the whole boundary to a single point such that the gradient is always either a rotation or a rotation plus a reflection.
Almost everywhere.
Almost everywhere, yeah.
So you can show it?
Because, well, it's clear when you make a fold, then, I mean, it's not differentiable on the fold. No, I can't show it, but actually, no, it's not so. In this case, you can actually do it, but I must admit I forgot the details how to do it.
Not mathematically, this piece of paper.
Well, okay, what you can show very easily is that you can get arbitrarily close. So simply you first make many folds one way, and then you make many folds the other way. So if you like, this question about effective behavior for the paper is very easy to answer, and it's very easy to see that all compressions are possible. But the surprising fact is here that you can map the boundary exactly to 0. And sort of the kind of analog of this in higher codimension is the famous mesh theorem, but what I've explained so far would only give you a Lipschitz map, and sort of the deep result of mesh is that you can make it C1. And you see here you have a chance because this set is connected where this is not connected. And in elasticity the sets are typically not connected. So that's why we work with Lipschitz rather than C1. Okay, so far so good, but here's some bad news. So I promised something about elliptic systems, and what I've said so far does not work for elliptic systems. Because if you take the set which was relevant for elliptic system, then in fact this set contains no rank 1 connection. So in forming this hull, you don't get anything new. And in fact, it's not surprising that it doesn't contain rank 1 connection, because you already knew that an elliptic system doesn't have a solution like this, where the gradient jumps across a hyperplane. So it seems that we haven't made any progress. And okay, here now is a new observation which was made by a number of people independently in seemingly rather different contexts, including 2 people at this university. And in our context, this observation amounts to the fact that you can construct interesting things even if the original set contains no rank 1 connections. And the idea is somehow to go to the bank and first borrow some additional matrices and later sort of pay them back. And so I try to indicate here how that works. So you draw this kind of inner square so that these, okay, I didn't say what this picture is. So this is a picture in diagonal 2 by 2 matrices. So the rank 1 connection are simply the vertical and the horizontal lines. And so you draw the inner square so that these lines extend. And then say you want to get a deformation where on the boundary you have this matrix P2. I could also start with something from inside the square. Okay, so P2 is not allowed, so I have to borrow it. But now I want to start paying back. So P2, you see, lies on the rank 1 line with A1 and P1. So I can split along this line, and this corresponds to a construction like this. So then I've borrowed P1, so I want to pay back P1. Well, nothing easier than that. I can split here. Then I have P4, I split again, I split P3, and I back to P2. But now I'm using P2 on a much smaller set, just on a certain fixed volume fraction, and nobody stops me from repeating the procedure. And by repeating this, I iteratively eliminate P2 completely. So what you get from this, if you sort of combine it with the analysis we already know, is that if you take any boundary condition in this inner square and the arms, and you give yourself any positive epsilon, then you can construct a map which is piecewise linear, so piecewise affine, and whose gradient takes values exactly on the 4 points. So this you can see here very easily, but it's in an arbitrarily small neighborhood. So what you learn from this, that the splitting you can not only do along rank 1 lines, but you can also do it along more complicated construction. You can start from a matrix here, and you can split it into sort of a neighborhood of these four points there. So now we have new hope for the elliptic systems. We couldn't embed a rank 1 line, but maybe we can embed sort of one of these T4 configurations. And actually so they're called, well, the one argument why they're called T4 is that because they consist of 2 T's. But the more realistic reason is because I first learned that from Luc Tortas' work. So anyhow, you can ask whether you can embed this picture in the set K, which comes from elliptic system, and that at least not immediately contradicted by ellipticity. And in fact, here's a simple example that you can embed such a figure. And to make it simple, we only look at the diagonal part of the thing. So we had here F, and then sort of here was the G, which is sigma times J. So if you restrict to diagonal things, they come out in this way. And the ellipticity simply tells you that sigma 1,1 has to be a monotone function of F11, and sigma 2,2 has to be a monotone function of F22. And so here's a particular choice, so you can subtract an arbitrary function of the other variable. So now let's ask whether we can embed a T4 configuration, for example, in the F11, F22 plane, where sigma is 0. And this simply amounts to sort of looking at the intersection of one graph over one axis and another graph over the other axis, and you can put almost anything on this intersection. In particular, as you see in this picture, you can put the 4 points in the T4 configuration. This actually does not give a variational example. If you integrate around this inner loop, you see it doesn't close, but you have to tilt the picture a bit. You have to look at a sort of tilted plane in this R4, and then you can make the example variational. It's a simple calculation, but due to time, I'll skip this. So this shows that you can embed one of these T4 pictures in the set which comes from elliptic systems. And so that means you can generate sort of additional points. But of course, we said, roughly speaking, we need to generate enough points so that we get an open set to apply then this inner approximation scheme. And of course, one T4 doesn't give you an open set yet. So what you need to show is that you can embed a whole family of these configurations. And that actually can be done purely by linear algebra. So let's look at it a bit more detail. So here I've drawn now a generic T4 configuration. So the essential feature of this configuration was not that it was flat, but that there's an inner square which is made of rank 1 lines, and then the points are obtained by extending the rank 1 lines. So this is what I call now a T4 configuration, and what the theorem would say, if you have this point, for example, here, then it can be generated through these other 4 points. So what I want to show is that I can find a family, if you like, of these quadruples, so that these corresponding points P1 run through an open set. And then I can sort of start the general machinery and do a little calculation to see that things work out. And to find this family is actually not difficult. So I simply define abstractly, I define sort of the set of all quadruples which form such a picture, and on the other set I look at all the quadruples where each point is in my given set. And so I'm looking at this map from the quadruple to this point P1, and I want to show that I can generate an open set this way. And this is done simply by a dimension count. So this is why I say this sort of PDE reduced to linear algebra. And so here's the dimension count. Let's first look at the dimension of these quadruples which form such a configuration. Well, they're very easy to parameterize. You can give yourself 4 vectors which are rank 1 vectors. The rank 1 cone is in 4 by 2 is 5-dimensional, 3 plus 1 scaling. So this gives you 23 parameters. Then you can decide how far you want to go out. This gives you 4 extra, then 20 is 24. Then you have a constraint that the sum of these 4 vectors is 0. But at the same time, you have the freedom to shift the origin, so these 2 cancels. So this set is 24-dimensional. Well, and the other set is easy because the original set K was a 4-dimensional graph in an 8-dimensional space. So this set script K is 16-dimensional. Well, and now their intersection in the quadruple of points, each point is in a 4-dimensional space, so the quadruples are 32-dimensional space. So the generic intersection is 8-dimensional, which is just the dimension of the original space. And remember, we wanted sort of a nice onto projection from this to an open set. So that the dimension count works out. And now you just have to show that you can really make this intersection transversal and this projection a local diffeomorphism. So this would amount to checking a certain 40 by 40 determinant, but luckily you can check it generically. I mean, if you can find some choice of quadruples for which this is okay, then it must be okay on a Zariski open set, and so therefore you're generically okay. So this, to cut a long story short, shows that there is such an elliptic counterexample where you can perform all these operations, and then you can make this very wild solution. Okay, so let's look a bit towards the future. So this construction depended strongly on the particular T4 configuration. But what was so special about T4? Well, if you look at it a bit more abstractly, what we really did is we replaced this lamination convex hull, which was defined by a set theoretic operation, by adding sort of convex segments to the hull, as you usually do in convexity, namely defined by duality. So the better object, in some sense, is what Matuszek and Plechurch call the functional hull, and that's simply defined by separation with rank 1 convex function. So point is not in the hull if you can find a rank 1 convex function, which is, say, 0 on the set and 1 on the point which you want to separate. And the function is rank 1 convex if it's convex on each rank 1. And using this notion, you can immediately see that the functional rank 1 convex hull of these 4 points in diagonal matrices is actually the whole square. Because, say, if you have a rank 1 convex function which is 0 on these 4 points, imagine you could make it positive anywhere inside. Then you can look at the point where it attains its maximum. Sort of by convexity in these 2 directions, the maximum must sit in one of the corners here. But it can't sit in the corner, because then the fact that if it sits in the corner, it can't be positive. Otherwise, the function would go first up and then go like this, so it can't be convex. So, and then what you can show is that the whole theory by Gromov, if you want to work in the context of Lipschitz function, can be extended from the lamination convex hull to this rank 1 convex hull, which is sort of a much richer, but also much less understood object. And so you may wonder, I mean, in some sense, the example, so-called example I constructed before was rather implicit, and you might wonder whether you cannot work with more explicit examples, and in particular, this notion of quasi-convexity on the one hand is natural, on the other hand, is defined by a non-local condition and so on. So it would be much nicer if one could do something in the class of so-called polyconvex functions, which was introduced by John Ball in the context of elasticity. And a function is polyconvex simply when it can be written as a convex function of the original matrix and all the minors. So 2 by 2 simply as a convex function of f and the determinant. And sort of the simplest polyconvex function in some sense I've written here, it's sort of simply f squared plus determinant f squared.
This is more general or less general notion of convexity?
It's a more restrictive notion. So every polyconvex function is quasi-convex, but not vice versa. And in some sense, it's much more explicit. So we try to look at this particular example. Here's again the set K. And now, from what we've learned, roughly speaking, if we can show that this set K is large, the rank 1 convex hull of that set is large, then there's a good chance for a counterexample, whereas if the hull is small, in fact, if it's just the original set, then that doesn't quite imply regularity, but at least that's a good hint. So we try to compute that hull, and in some sense, so far, we failed. Even in the simplest case, when you restrict to diagonal matrices to get some feeling, then you get something like this, and then sort of the 2 rank 1 directions are here and here, so rank 1 convexity is really separate convexity in R2 plus R2. So that's now becoming a very geometric notion, but even that was hard to decide. For, interestingly, in some sense, the hardest case where we have the least convexity, when this term is not present, we could do, even in full generality, but when this term is positive, the best result is known currently is one by Kirchheim, which says that if you have a finite subset of this, then this hull is trivial. And then finite really matters because it's sort of a marching separation argument, and it's important that sort of you can look always at the next point you want to separate, go for it, and then go on. And what you can show quite easily, that whenever you try to make something polyconvex in 2 by 2, these T4 configurations cannot be there. So this shows that polyconvexity is more difficult. Now here is a very recent result by a PhD student of mine, Laszlo Skerlihidi, and he actually, at least abstractly, showed that there's even a polyconvex counterexample. And he does it in a very interesting way. He didn't start from choosing a particular function and trying to compute the hull, but he did it the other way around. He started from a TK configuration, which is like T4, except that you can have more than 4 points. And so, assume you had fixed the point, he's trying to look now for the polyconvex function. So in other words, he's looking for a convex function G, such that the function f defined this way sort of will have the right relation. And I've written here with the j on the other side. So that's simply a relation for this matrix G at very special values, namely at the values fi and that fi at k points. So what you now do is you somehow regard the values of the function G at these points and its derivative as free parameters, and you ask whether you can A, satisfy this condition, and B, extend it to a convex function. But the condition to extend it to a convex function is just the obvious one. So if you give them the values and the slopes, and all you have to check is that you satisfy the condition of convexity sort of for the discrete points, then you can extend. So satisfying this and convexity simply becomes a set of linear equalities and inequalities. So it's a linear programming problem, which you can check, for example, on a computer. Finding the points is a nonlinear problem, but if you consider the points as given, say choose them randomly, then it's very easy to check whether they give a feasible system, and sort of actually not by complete trial and error, but by first cleverly exploiting some symmetries and looking for some good candidates, Laszlo actually found such a quintuple of points for which this is possible to solve, and in this way he found polyconvex counterexample. So that shows that even Ball's notion of polyconvexity, which is very natural in elasticity and which is very natural for minimizers, is not good enough to get regularity for general equilibria. So that brings me to the end. So what I try to explain is a new approach where essentially you have one abstract general theorem which says if a certain convex hull is big enough, then something interesting happens, and then all you have to do is sort of linear algebra, but actually, so this is the selling point, but the truth is that I think there's also a lot of combinatorics and other discrete things involved. And in some sense what gives us hope is that already the first non-trivial configuration which was known, namely this T4 configuration, led to interesting results. And needless to say, there are kind of many open problems. So one would be, for example, to find a more explicit example. But I think the biggest problem in the background is to understand the geometry of these new notions of convexity, and also actually to have, say, efficient algorithms to compute these convex cells. I mean, for convexity, we have very efficient algorithms, but they're all based on sort of, in some sense, on separation by hyperplanes. And here, the functions we can use to separate are not all explicitly known. We know some rank 1 convex functions, but we don't have a complete list. And on that, let me close.
So what is the connection to crystals?
Well, so the connection to crystals is that, for example, I had this question 3, what are the effective properties? So what cannot be the most important questions for the crystals? I think the most important question for the crystals is to understand this approximate solutions, and there sort of essentially the same objects come into play. So that's, what I talked about here, exact solution, was sort of, as I said, more applications of some ideas we had learned in studying this question back to sort of, back to PDE.
Approximate solutions are the minimizers.
Well, the approximate solution by definition are kind of sequences which approximate better and better. And if you want to talk about the limit, if you want to talk about the limiting object, then the limiting object in general will not be a function where the gradient only takes one value, but will be so-called generalized function or Young measure, where the gradient where the gradient should be viewed as a map not to a single point, but to a probability measure, a distribution of possible values. And then these limiting objects can be viewed as generalized minimizers, but the regularity questions then are kind of a different kind.
So these minimizers, you have this convex integration. You use this.
No, this convex integration is really something which is used for constructing exact solutions.